Okay, guys, I hope that first video on limits at infinity and the background from Algebra 2 and Pre-Cal was helpful. We're going to go ahead and move on to the more robust way of actually dealing with limits at infinity, which sometimes is necessary and most of the time is unnecessarily long and complicated, which is why I've titled this short video, Limits at Infinity, the Unnecessarily Long Way. Sometimes, okay? Now, the first thing we need to start out with is a theorem, okay? And the theorem states that the limit as x approaches infinity of 1 over x to the n, okay, so long as that power is positive, right? Because if the power is negative, then it just pops back up to the numerator, and then of course it goes to infinity. So long as this power, while x to the n is in the denominator, is positive, okay, this goes to 0. And that should make sense to us, okay, because we've actually walked through that numerically when I was giving you the case for how n behavior asymptotes behaved on rational functions to begin with. So we've gone over something like this in Algebra 2 and Pre-Cal. Numerically, it should make sense. Now it's just formalized into a wonderfully underwhelming theorem, but it does actually give us a little bit of leverage in terms of moving forward. So if I have something like, let's go ahead and use the problem that we started out with last time. Let's say we have the limit as x approaches infinity of 3x squared minus 4 over x squared plus 2. And actually in the last lecture, I'm not even sure we actually evaluated that limit, but let's go ahead and do it now. Now, I need the terms in here, some of them at least, to start resembling something like this. So what we need to do is we need to basically figure out what the largest power is, and then, let's turn that into multiplication, we need to multiply through by its reciprocal. And if we do that, we wind up with the limit as x approaches infinity, and of course we're going to take this and we're going to distribute it to both terms in the numerator, and we're going to take this and we're going to distribute it to both terms in the denominator, and when we do that we get 3 minus 4 over x squared, 1 plus 2 over x squared. Well, I tell you what, that term and that term all of a sudden look eerily like this. So those two both go to 0. And what's left? What's left is the ratio of the leading coefficients, okay? But now I've actually done that using a theorem and limits and done it all kind of rigorous-wise. But that is basically the method that we're going to use in order to figure stuff out, okay? So let's go ahead and do a few more examples. We'll get to the really nasty ones probably in another lecture. Now let's go ahead and do the limit as x approaches infinity of 9x squared minus 2 over 6 minus 29x. Now we should already know that this is not going to be a horizontal asymptote, right? We know that the degree of the numerator is larger than the degree of the denominator, and therefore in order to find the actual asymptote, the end behavior asymptote, which in this case is going to be linear, we would actually have to do the division. But to actually show that, okay, we take a look at the largest power, and the largest power is right here, it's the x squared. We go ahead and divide by that, okay, and we wind up getting the limit as x approaches infinity of 9 minus 2 over x squared, 6 over x squared minus 29 over x. And now I have 3, right, 3 pieces that actually go to 0. Now I notice that and you would have to reason it out in here. This is actually going to wind up going, it's actually going to wind up going to negative infinity as you're going after positive infinity on the input. And that has to do with knowing what the division is going to give you. the division is going to give you a linear with a negative leading coefficient. And of course, anything linear with a negative slope slopes down and to the right. And of course, numerically, we ought to be able to figure this out as well. Because as we plug in infinity into here, 2 over x squared and 6 over x squared are going to get smaller faster than the 29 over x. So if 6x squared is getting smaller faster than the 29 over x, then 6 over x squared minus 29 over x is a smaller minus a larger number. Well, smaller minus larger is always negative. So it's 9 divided by a number that is increasingly approaching 0, but it's increasingly approaching 0 from the negative side, and therefore we're going to get negative infinity. Now you just need to determine whether, like, what your teacher wants, because we've talked about the preferences of infinity and does not exist and stuff like that. She may not even give you something like that that doesn't have a horizontal asymptote, but you need to be very careful about asking the teacher about their preference and giving the teacher what they want. Now let's go ahead and do another one. How about the limit as x approaches negative infinity of 5x minus 9, 4x cubed plus 2x plus 7. Now, what is the largest power here? Well, obviously, it's the x cubed, okay? Keep writing an equal sign, and I should not do that. 1 over x cubed winds up being the thing by which we need to multiply. Sorry if my voice is failing you guys. It's kind of late at night here in Scotland. And it's kind of been a long day, too. So... and all of a sudden, as I multiply through the 1 over x cubed being the reciprocal of that largest power here, the only thing that's not 0 is this 4. That goes to 0, that goes to 0, that goes to 0, that goes to 0. I ultimately have 0 over 4, or 0, and that's how I actually evaluate that limit. Now, notice that I said that it was unnecessarily long sometimes. Okay, well, here comes the sometimes. Now, let's say, for instance, that I am given f of x is equal to the square root of 36x squared plus 7, okay, over 9x plus 4, okay? And let's say that I'm not given a limit, I'm given a function and asked for the end behavior asymptotes. Now, in the last video lecture, I showed you that for the one that was given, where this question was asked, it was the same on both sides. But that's not the case here, okay? So we have the limit, and I'll show you why, okay? Now remember, when I'm given, because of the convention of radicals, when I'm given a radical, I know that the radical always gives me a positive output. And that's fine as long as I'm going to positive infinity. But what happens when I'm going to negative infinity? Well, that radical in the numerator is going to continue to give me positive outputs. But that one in the denominator, that's not a radical, nor is it squared. It's going to start giving me negative. So what I have here is a function that actually gives me different end behavior asymptotes on either side. And that has to do with the positiveness and negativeness that's possible in the denominator and not possible in the numerator. But let's go ahead and walk through this. Now, when we're dealing with this, I know, because of the sort of hints that I gave you in the last one, that when I try to evaluate the degree of the numerator, I recognize the fact that that degree is the first degree. Now, it's not capable of being simplified, but that's a quadratic square rooted. A quadratic square rooted is a first degree, okay? And I know that that x squared right there is actually x squared square rooted. So the highest degree term is both the 36x squared, which in reality is a first degree term, and 9x. So what I'm going to do is I'm going to multiply that denominator by 1 over x. But I'm going to multiply the numerator by 1 over x squared. Now, if you remember, 1 over x squared is the same, or square root of x squared is the same, okay, as the absolute value of x. So this winds up being the same thing as 1 over the absolute value of x and 1 over x. Well, if we're going towards positive infinity, we're plugging in positive numbers. It doesn't really matter, okay? And therefore, this simplifies very quickly into 36 plus 7 over x squared, 9 plus 4 over x, okay? Well, as we talked about before, that right there and that right there fit my theorem. They're going to 0, and what I'm going to get is root 36 over 9, or 6 over 9, or 2/3. So the end behavior asymptote as x goes to positive infinity is y is equal to 2/3. Okay, well that's kind of nice. Well, let's talk about this one. Because we want to do the same move here. We want to multiply by 1 over x. But you have to remember that 1 over the square root of x squared is 1 over the absolute value of x. So if I just leave this as is, I'm multiplying by -1. And I can't do that. That changes the value, right? Because this ratio is the same as this one. This ratio for positive, this whole ratio, for positive inputs is +1. That identical ratio for negative inputs, because I'm going to negative infinity, that whole ratio for negative inputs is -1. And therefore, I need to go ahead and plug in a negative somewhere in there in order to flip it back to +1, such that I'm actually changing the form but not changing the value. Well, that's very predictable in what it's actually going to wind up doing, okay? And we wind up getting the square root of 36 plus 7 over x squared over -9 minus 4 over x, not x squared, but just x. Now, that and that are still 0 as x goes to negative infinity. But now I get a root 36 over -9, or what winds up being a -2/3. And I have used my limits at infinity in order to do that. Now, some of you are kind of thinking to yourself, is that really true? Well, okay, let's go ahead and I'll prove it to you, okay? How do I do this again? Square. 36x squared plus 7 and 9x plus 4. And if we sort of move it just a little bit, we're going to see that y is equal to, and let's go ahead and zoom in just a little bit, okay? We're going to go ahead and see that. And if you want to, you can go ahead and add a new equation and do 2/3, and then add another equation and do -2/3, okay? And if you go ahead and highlight them all, you see the fact that as it goes off to the left, it does hug this y is equal to -2/3. And as it goes off to the right, it dips down below, but then it turns around and starts hugging it from underneath as it goes off to positive infinity on the input, okay? So our analytic work matches up with this graph, and therefore that winds up sort of verifying our work right here. Now, is that fun? Well, not really, okay? But is it doable? Sure. You just need to be very, very careful that this is only, this negative right here is only really a big deal if you have a square root, right? Because that convention for square roots is there because cube roots can be positive or negative, right? And therefore, if you had something analogous, let's say that we had g of x is equal to the cube root of 3x cubed plus x over x minus 4. This is still first degree over first degree, but a cube root doesn't spit out a positive all the time. If it's negative, it spits out a negative. If it's positive, it spits out a positive. And therefore this one, you won't get two answers. This one, you'll actually just get one. Okay, it'll be the same to the right and to the left. But remember, odd roots behave differently than even roots do. And that's the reason why you have to make this allowance right here, such that 1 over absolute value of x and negative 1 over x, ultimately on the negative end of the x-axis, wind up giving you 1. Okay? Now that gets us over about 15 minutes. I'll line up a couple more examples and a couple that are not necessarily polynomial based like these, such that we can sort of get a firmer grasp of limits at infinity before we round that out and move on. And I think the next subtopic is the limit definition of derivatives. So we have that to look forward to.